happy to be here. Talk a little about how do we run massive scaling mobile games on Microsoft Azure. And my name is Kalle Hiitola. I come from a company called Next Games. I'm the CTO of the company and also a game developer. And just to share a little light on what is Next Games, we are a Finland-based free-to-play mobile game company. We were founded in 2013, so a relatively new company. We have published 2 games. The first one was Compass Point West, which was based on our own IP, and the second one was The Walking Dead: No Man's Land, which is based on the TV series The Walking Dead. And to mention something significant that happened to the company, probably one of the biggest things was that we were the first gaming company to go public in Finland. So that happened about a year ago. And now currently we're working on with the new Walking Dead game called The Our World, which is location and AR based. But today we're more talking about how we built the system to run the Walking Dead: No Man's Land. We have around 500,000 users each day for that game. We generate quite a lot of data on that because we're tracking each and every move of the players. You know, analytics data is very important for free-to-play games. We really need to know what's going on with our game and how players are behavior, so we can adjust the game and keep on evolving it. And we stress quite a lot of the database also, but thanks to for example Cosmos DB, that kind of number doesn't even pose a problem for us. And then the gamers themselves are pretty active. As you can see, we kill about around 43 million walkers per day. So if everybody in the US would turn into a walker, we could get them done in about 2 weeks or so. So doing well in that sector too. So to go a bit more in detail, how did we build our system? Here's a high-level architecture view into our setup. So the way we have built the backend for our games is that we started off with the idea that we want to create a generic backend that we can share between different titles, so they can use the same technology, so we don't have to always do the backend work for each of those games. So we build our games on top of Unity, and of course then our main platforms are iOS and Android. And the main technologies that we use there for our front servers, which are basically running the whole game logic, they are built on top of cloud services, and most of our auxiliary services are also running on top of cloud services. Then also we have some of the services are running on top of web apps, so all of, for example, our dashboards and things like that are on top of the web app. And for some of the external stuff, we choose some external partners because we feel like one of the philosophies is that you don't have to do everything by yourself. It's more important to have just the right tools for it. And especially Azure gave us a lot of these tools to work with. And in order to store the data, we used Cosmos DB for all the metadata of the players, and then we used blob storage for actually storing the state of the player. And then for analytics and things like that, we use Event Hub and then like other services like leaderboards, in-app purchases, and those heavily relied on Cosmos DB. So when we started to build this system, we set some of the design goals that we want to have there. Firstly, as I mentioned, we want to have one platform for different kind of games, so we want to make sure that it's so generic, it doesn't really care what kind of mechanisms the game itself has. Does it have a guild? Does it have a leaderboard system? Does it have, within the guild, is there some sort of promotion that you can be a leader of the guild or not? We didn't want to do any of that, so we made it a really generic system that gave to the game teams the possibility to decide on this. So basically it was more or less a server development environment for the game teams instead of just like a black box that does things in a certain way. So as of that generic approach, of course, whenever we create a new feature, all of the game teams would benefit from that feature. So if for one game we created a social feature, that would be also available for the next game team. So it does reduce the time to market because they don't have to reinvent everything all over again. And we wanted to make sure that we have top-notch dashboards for our marketing and player support, because those are the most important parts for running live operations. We need to have flexible tools where you can do promotions, run events, and also care about the players, that they really feel that they're being looked after. So if something goes wrong, we want to be able to communicate with the player and show them that we have fixed the problem. So why we started to do this is how we started to do this. These are the design pillars. So we wanted to make sure that we let people focus on making games instead of technology. So we tried to keep the amount of tech as small as possible. We want never to rush the client, because we feel that games are becoming more and more social and more competitive. So you have to make sure that it's fair for all the players. So there's no possibility for cheating. And when we started off thinking about how do we want to build out our server infrastructure, we wanted to keep scaling in our mind as one of the foremost things that we need to do. And live operation was also something that we wanted to think about from very beginning. So going live is just the beginning. So I want to go a bit more in deep of each of these pillars and tell about the lessons that we learned while we were trying to achieve that, and how we move forward from there. So if we go deeper into we make games, one of the things that we decided as one of the strategy was to use existing services, and Unity, for example, was one of those existing services. We didn't want, when we started off the company, to start battling with our own game engine. We wanted to make sure that we were able to run on an engine that we can trust, and we could feel like it's becoming like more or less industry standard by now. And of course, it really helped because we like C#, and you can write scripting on C# with Unity, so that was definitely one of the big things to choose there. Now, another thing is that use existing services, that you don't have to do everything by yourself. We choose quite a few partners to partner up with in order to deliver some of our things. For example, we didn't want to do all the monitoring tools ourselves. We used Datadog for that. We didn't want to, for example, to do all the support tools. For example, the way of communicating with the player, having ticketing system on top of that, Helpshift is a great tool for that. So we just wanted to embrace those and just include those into our own dashboards and make sure that we can communicate with them. And then for example, with logs, we use log entries because we eventually had our own logging system, which was nice. I made it myself. It's real time, flowing log and everything. But the feature requests just keep on going. Could I get a regex search for here? Could I use SQL to search here? Could you do a dashboard that shows how many errors is where happening? And could I have them split in by servers, by players, by whatever? So quite quickly I decided this is not the road we want to do. We are not the log, parsing company. We're a gaming company. So we choose to use some provider for it. That being said, even though we choose a lot of pre-existing games, there was still a lot of tech to do. So we need to make sure we are scalable and we have a secure backend. So we make sure that all the communication is done in a way that no one can interrupt it or cheat on top of it. We also want it to be global, so we want to have the capability of have global leadership, global chats, if that ever makes any sense. 10,000 messages per second in a chat window isn't really a useful thing, but at least you have the capability if you want to go that crazy. We need to build our own analytics. We started off with pre-made analytics, but we quite quickly figured out that the data is so valuable for us, so we really need to make sure that we own the data and have always access to it. And we also want to have the raw data available, because it's very common that we figure out that we should be able to analyze some piece of information that we didn't realize was important before. So if we have the raw data available or the raw events available, we can replay those events and recreate the necessary data from that data, at least most of the times. And still, we still need to build these live tools for supporting marketing. Well, here's what we learned on that sector is that selecting the right tools is really tricky. For example, as I was telling, we thought we could use analytics tools ourselves, but pretty soon we figured out that that we need to do it ourselves instead of using a third party. And same thing with log handling, the other way around. So you never know what is the best choice for you, but at least you have to be open for the idea of changing things that you did yourself into an external service and vice versa. And the resisting temptation splitting tech and game was probably one of the biggest lessons that we learned there. Our tech team thinks they always try to think about the things from the game's perspective, but that doesn't always that just simply isn't enough in most cases. We learned that it's way more beneficial to actually take all the tech people who are creating the backend and put them sit into the game teams and be really next to the customer who's using the system, and not only guiding the customer or the game team developer to use the system, but also doing parts of the game features that use our backend directly in the game, because that way they learn themselves what kind of problems they could be facing, the game developers could be facing, and how they have actually solved those things on theoretical level, but in practice that could be that the solution isn't viable enough. So one of the biggest things is to never trust a client. So the way we wanted to build our communication stack was that we should be able to send all of the communication in plain text so everybody could read it, and still you wouldn't be able to hack it. And in order to achieve that, we need to be running the game logic on the server side and the client side. And the server side needs to be an authoritative part of that combination. So we ended up creating a deterministic model. So when we talk about a model, it's basically the game logic running on both ends. And how do we do that is that we actually have the very same pieces of C# code shared between the server and the client. So we don't need to rewrite the validation code for the server separately. We can just use the exact same files. There's actually a Git submodule that we use. So to quickly go through like how the data execution model connection happens is that firstly the client connects to one of the servers. It will get a specific address back, so within the cluster and throughout all the traffic managers and load balancer, it will get a specific instance address for it. So we now have basically the game is guaranteed to connect a certain instance, and if there's a connection problem or anything like that, it can return to that instance because it knows the specific address. Of course, the instance go down, then it will start over when it notices that okay, there's no way of me connecting to this instance. So once the client has done the initial connection, what we do, we reload a JSON file from Azure Blob Storage and parts of it from Cosmos DB, and that will become we boot up that as the game logic. So now we have a running instance of the game logic on the server side. So once that is done, it's up and running. We serialize the results from that. It might be that we do some changes for the state of the player while we're loading it. That's why we need to serialize back. Of course, it's optimized in a way that if we don't do any changes, we don't re-serialize, we just use the same one. So then we have the game logic running on both ends. Now, if we want to do any changes to the game logic, what we need to do is create a command that will interact with the game logic. So this is a very common pattern. So basically, the game logic will then execute the command or whatever content is within the command. It's just a simple C# class that can basically interact with however it wants with the logic. Now, in this part, the client will do a quick validation, actually the same validation that the server would do, so it will validate it is a valid call. So for example, if they're collecting resources, are they collecting right amount of resources or anything like that. So just making sure that the data that the game logic has matches up with the commands that it's getting. Once that's done, what we basically do, we put them in a queue and then asynchronously start sending them to the server. The reason why we do it asynchronously is that we don't want to wait for the server to answer, because that would give us a sluggish user interface unless we're really close to the server. So as we do it asynchronously, and as the models are deterministic, so whatever values we put into the model, they always come with the same result. So it doesn't matter that it's happening asynchronously in this case. So then basically we just put it as JSON, we put it command in, and then we execute the same stuff on the server side. So now we know, has it been validated? And there's all sorts of patching and things like that going on just to make sure that we don't have to sort of wait for the answer for each of the commands. We have different kind of commands. Some of them need to be answered right away. Some of them can be patched. So it makes it even more robust. So now, as the server executes command, it will then basically just return Boolean back to the client saying, if it's true, everything's fine. If it's false, something went wrong, you need to reload your state from previous save. So then it's up to the client, can they actually hot load it, or do they need to reboot the loading sequence? And eventually what happens is that when the game disconnects, we will just reserialize the player into the blob storage. And as I mentioned earlier, why we do this, firstly, you don't have to write separate validation code. Often you need to write quite a lot of code in order to validate. If you have, for example, you could have a Java backend or JavaScript backend or whatever. You either go converting your C# code into that language, or you run, even if it would be supporting C#, we would still write a separate validation code because you would have the same context available. In our case, we have all the same context available on server and client, so you don't have to write any separate validation. Reduces time, reduces resources needed within the game team. We don't need a separate server coder that would actually write the server side of things. Asynchronous execution with Qt, so that help with the deterministic modic we can do that. We can rely on that things will go the right way. And of course, one of the very nice thing about this is that we can hotfix the model, the logic on the server side, and fix the results that it gives. So we can, if there's a bug that we introduced or something wrong with the data that we have, we can hotfix it without actually updating the client. Although the client would still be running with the old version of the logic, it doesn't really matter because we can still sort of fix the problems on the other side, on the server side. The worst thing that could happen is that then the client would need to reload in certain stages to hit the bug, but at least they'd be able to continue playing. So what we learned from there. Firstly, mono and micro CLR, they don't work the same way. That was a very good lesson to learn. It took us a few really long nights to figure out, for example, that lists are not always in the same order. It is really hard to detect this kind of problem. But after banging your head against the wall for 3 nights, you figure it out. So something to be aware of. Obviously, floats don't work the same way. You have to do all your math in fixed point. So that's of course something to consider if you're thinking about using this kind of approach. And of course, as we are working with the same context on server and client side, it's very important that you design your data structure really well. So you're sure you have the necessary data available and all the content available on both sides, and it's clean and easy to update. Otherwise, you end up in a situation where you have a monolithic game economy data sheet, which is really hard to maneuver with, and it's really hard to know anyone to follow. So it's easier for chunking that into smaller pieces and working with smaller pieces. So, scaling first. So how did we achieve our scaling? Of course, this is our previous architecture that was relying on cloud services. Currently, we're working on a new architecture which is based on Service Fabric, so our approach there is a bit different. But this is still valid things for the No Man's Land game. So firstly, with scaling first, we sort of set up this philosophy within the server team that nobody should be trying to figure out first how to get things work and then think about scaling later on. Because you shoot yourself in the leg pretty quick with that. Hey, I got it working, now it's just perfect and beautified, and you just need to figure out how to scale it. Will never happen. So we started off how will we partition things, how we will scale things out, how we make sure that everything's horizontal and we don't have a single point of failure. So, for example, as you can see from the diagram, for connectivity, what we did was that we have a traffic manager that handles the load balancing between different cloud services, and as cloud services is just a bundle of managed virtual machines. We had a ton of cloud services behind that, and from there, within each cloud service, we had like 20 virtual machines. So I think when we launched The Walking Dead No Man's Land, we had around like 40 different cloud services, and each of those had like 20 virtual machines. So it's quite a lot of computers, but we didn't know how popular the game is going to be, and we want to be prepared for anything. Of course, we could then, as we saw how the system was working with the load that we were getting, we could scale it accordingly. So with this kind of mechanism, we can now return the address of the single instance and make sure the player is always connected to the same instance as long as the instance is alive. So in a sense, we're gonna have it there. And why do we want to make sure that we have the player connecting the same instance? Is that we want to load the player in the memory of that instance. That is the fastest way of reaching the player state. So we keep every player in memory. So even though our instances are more or less stateless, they become really much stateful for the player because we are keeping the actual object in memory. We just simply put them in a dictionary as an object. It's way faster than serializing them to, let's say, to Redis cache or any other cache, because in that case you would always need to deserialize and serialize in order to access them. And the reason for that is that we're very CPU bound. Now, as we're working on JSON, and the player data can be up to 4 megabytes, you can imagine that will turn down your CPU performance quite quickly. So, in order to avoid that, we need to keep those in memory. And even though that we kept those in memory, we would still be CPU bound, just because when we're storing them, once the session ends, it's so heavy. That's just mainly because we have a really large player states to serialize. There's not only all the sort of the variables there, but there's also parts of the logic there. So it grows those into being bigger than you would normally see. So, of course, to store this, partition is your friend. You know, we store this in Azure Blob Storage, which is very great to store any sort of static files. It has some limits to it. You can only do 20,000 requests per server. Actually, that is 2,000 requests per partition, but usually not a problem because each container is their own partition, so it's super simple to work around that. But the 20,000 is a bit harder. We aimed for 1 million concurrent users, and in order to make sure that the storing of the player is achieved, we overcome the problem of having only 20,000 requests per account by creating 96 storage accounts. So it's a bit of, outside of playbook solution, but it works pretty well. It's not the prettiest one because you have to have 96 storage strings somewhere in the system, which is definitely not a nice thing to have. So, for social features, in order them to scale, the way we did it was that we also run our social states in deterministic models. So, what that means that we can also run in async matter. So, basically, how our social system works is that it is a distributed messaging system that just guarantees the order of delivery for each model, wherever the model happens to live. And that model always lives on the front servers. So the client sends a normal model command that has a server call that send a social message. That send a social message will then distribute that content into our social server that will know which players are subscribed into this social model and which front servers are hosting these social models, and that will handle the distribution of the social message into those front servers. And then the front servers will execute those commands in order and for all the players, and then they will send it forward to the players' devices so they can see the changes in real time. For example, for chat or anything like that. But with this system, you can, because we don't care what the payload is. So the payload could easily be a chat. The payload could be giving an item to another player. It doesn't really matter because they're all sharing the same social model. So the social model can hold shared inventory, shared state between the players. And every player can have as many social models they want. So it gives you scalability. So how to test this? Well, we used to use, this is back in 2014, 2015, we used a lot of Visual Studio Online to do the testing. They had a lot of great tools for load testing. Basically, you just set up a unit test, you record, as we're based on commands, it's really easy for us to record each and every command that the player session has, and then just play back that in a unit test that will do a little bit of time randomization in between, a little bit of randomization with certain values, but other than that, just running in parallel. So you can have one unit test running a few thousand players, and then you have a tons of those spin up in the Visual Studio Online load testing harness. So what we learned? Well, load testing, load estimate is almost impossible. We need to be flexible with it, so we need to have a lot of flexibility. Testing is hard. Our setup of load testing was a bit consuming on the Visual Studio Online testing tools back in 2014. We crashed the system, but you know they have come a long way from there. So I'm sure it works better now. And we also, what we learned from load testing is that we need to be able to scale different services within a different space. You know, we might notice that we need more front servers, but then actually we don't need that many of analytic servers, for example, or social services. So we need to be able to scale them and have tools that will detect when do you need to scale and what. So on design pillars, this going live is the beginning. It's sort of my favorite quote among developers because often, like the good old games, the old word was let's ship it and that's the end. With the new games, it is more about let's ship it and that's the beginning. Now the fun part starts. Now you have to start really thinking about how do you going to grow your game. For example, with the No Man's Land, we introduced player versus player mode into the game after the initial launch. We introduced new characters in there, we introduced new live events in there, we introduced new bundles in there for the players. So you have to have tools in order to keep the game alive without always updating the game. That's one of the lessons we also learned, is that if you update the game too often, and as we have a 350 megabytes worth of download, people don't tend to update that keenly, so we need to be able to run multiple versions simultaneously. So when we do a mandatory update for the client, we would still need to actually run the previous version, so all of the clients can still run and still play, but some of the features will be deprecated from them. So, and of course, you need to be able to deliver content. So what we did was we created this system where we have a dashboard that will have all sorts of different content. We don't, from server perspective, we don't really care what the content is. We don't want to sort of dictate that you have to have news, you have to have announcements, you have to have banners, you have to have this and that. For us, content is just content. It's generic content. The game itself defines what kind of content they want to have, and based on that we have that on the dashboard. And then we have a controller which will handle always the actual publishing. So the CMS, the dashboard itself, doesn't actually take care of the publishing. It's the controller that makes sure that all the pieces and information is in the right place on the right date and right time. And then we need to be able to distribute that in a different ways. So for example, we do support video content. So if the game wants to digest some kind of video or show video to the users, we use Azure Media Services to distribute that. For bigger assets, we use CDN, and for smaller things, we use our servers that and directly just deploy that content for the players. So from game's perspective, what we learned is that it's very important to start thinking about the live operations from the get-go. We need to understand what kind of tools are necessary there, but also we need to really understand how the live operation will be operated once the game is live. It's not about, it's very sort of it's always hard to design a game, but it's even harder to think about beyond the point when you go live. And then there's often sort of the situation where you have, for example, when you design the data structure of your game, it's easy to design the data structure when you're developing, so it supports development. But at the same time, it might be the situation that in future, once you go live, that data structure doesn't fit the needs of your live operations. So you have to really think about those live operations beforehand. Otherwise, you will be stuck with the data structure that very well suits you in the development phase. But as this game is going to be live for years, you will be stuck with a very problematic data structure. So you need to think that from the very beginning. So those were the key learnings that I had to share with you. And then I want to share a little bit of our future, where we're taking our technology forward. So we are definitely moving into Service Fabric. That is going to be our next platform that we want to run on top of. Of course, we're going to use other technologies from Azure, like Azure Functions, to run some of the sort of more of cron job kind of things. Also, we are using Web App. Even more, we're using Event Hub, Cosmos DB, and things like that are getting more and more involved. What we also want to do is closing the feedback loop. So we want to be making sure that all the analytics data that we have, we gather tons of analytics data, but currently the way the analytics work is that you have some analytics data, you create a report, then you go and you think and ponder what should you do with this analytics data, and you do the change, you do an A/B test. Instead, we want to close this in a way that we want to do tests with the analytics data that it could affect the game immediately, based on machine learning and artificial intelligence. We can easily do tests that will test different values as long as we have certain KPIs that the machine learning and AI part can follow. So they can change values that the humans wouldn't ever sort of even detect that has a difference. So that's definitely some of the key areas we want to focus in future to make sure that we have really rapid feedback loop. And we want to be better in abstracting for games. So as we were building our current platform, we needed to cut some corners. So not everything was really abstract from the game's point of view. Now we're moving forward into a world where the game is actually just a package for us. We have a game image package. So basically, no matter what you used in order to run the game, we can now run it in Service Fabric. It can be just executable, it could be Node.js, it could be C#. We just have sort of set of interfaces that needs to obey, and we have a way of packaging it, and we have conventions and rules how do you package all the necessary information associated with the game. But yeah, that's how we built the system. So thank you for everybody to listen. I hope I shared some valuable information for you, and thanks.